All right, everybody. So what we're going to be looking at today is section 2.2 in the book, set operations. So in the previous lecture, over the last two lectures, we managed to cover most of the basic definitions of sets, but we stopped at the end of section 2.1. Now what we're going to do is move on to section 2.2 here, which is just going to be more operations we can do with sets. Now, something from 2.1 that we're going to need is going to be this definition here. So recall this. So we'll just say recall. Recall. What are we going to recall? We're going to recall that if A equals B, actually, no, not quite that. A equals B, if and only if, so those are sets, A should be a subset of B and B should be a subset of A. So sorry if my handwriting's a little worse than normal. I don't think it can afford to be worse than normal, but it might be anyway, just because my iPad has 2% battery life and the cord barely reaches. So it's kind of at an awkward angle for me. But anyway, let's get going. All right, so we're going to be looking at this definition, or rather we'll be needing this definition maybe at 1 or 2 points today. Also, here's another thing. I'll say recall again. So we have a definition of the top definition here says that A equals B if A is a subset of B and B is a subset of A. I should say it in words. Now the other thing that I want is if, what do I want to say? What is the definition of a subset? So if, or again, I keep writing, I want to start at if, but I want to use an if and only if. So I want to do A is a subset of B. What does that mean? If and only if for all X, if X, that's the wrong symbol, let me fix that. X in A implies X in B. Okay. So that's a definition of subset. And I don't know how much we're going to rely on those, but I know it might be at some point. So let's just get them out of the way. Okay, so now we can start actually section 2.2. So the things that we're going to be talking about in here are things that you may know something about already. Unions, intersections, complements, and that's mostly it. But yeah, that's mostly it. So let's get going. So here's our first definition from section 2.2. Definition. So let A and B be sets. I'm probably going to keep forgetting to write that, but you know that that's what we're talking about. Let A and B, let A and B be sets. Okay, the union of A and B, which you write this way, A looks like a U, but it's not. The union symbol. A union B is the set that contains all elements that are in either A or B. Okay, so what that's saying in symbols is this. So A union B is equal to, in set builder's notation, it's the set of all X such that X is in A or X is in B. Okay, and we can also draw the Venn diagram so you can see what that looks like. What am I doing here? Draw the whole rectangle and then I can resize it. Okay, so the idea is you've got a set A and then you've got another set B. So let's call this A and this B. And then you want to say, well, what's the union of sets A and B? Well, it's actually just going to be the area inside of both of those circles together. So like all of this. I'm not going to color that in nicely, so sorry. Oh, that's getting worse. I need to stop. I need to stop. Okay, I'm stopping. So that's the area that we're talking about. All of the area that's inside. So everything in A and everything B in B together combined. Okay, and that is called the intersection. So where does it say that? I said union, not intersection. Union of A and B. Okay, so yeah, let us have another definition, and then we'll look at these in more detail. So the next definition is the intersection. I'm not going to write let B, A and B be sets. I'm just going to say the intersection of sets A and B, denoted A intersect B. Looks like an upside down union symbol. A intersect B is the set. Come on now. Is the set of all elements that are in both A and B. So I think maybe I want to even rephrase that. So all elements that are common to A and B, right? If we write it out in symbols, A intersect B is going to be the set of all X such that X has to be in A and X has to be in B. So that's different than the union, is that this is an and, whereas up here it's an or. Okay, so that's the difference. So what's that look like on a Venn diagram? Oops. Try again. Stop. Got an A. Got a B. Doesn't have to be smaller. So what is the union? Sorry, what is the intersection? So the intersection is in here. Just the part that's in the middle. Okay, so this is, I should write it. Can I write it? We'll use black. Nope. Okay, so that's the shaded area of A union B. Whereas this one, this is A intersect B. Okay, so in order to be in the intersection, you have to be in both A and B. And in order to be in the union, you have to be in A or B, doesn't matter which. Okay, and so those are the union and the intersection, the two most basic set operations that you can have combining two sets. So yeah, so let's do an example here. There's not a lot to do yet, but we can do something. We can do, let's say, example. Let A equal 1, 3, 5, and B equal 1, 2, 3. And I'm going to say find A union B and A intersect B. So we want both of those. Okay. And so what you're going to do is just use your knowledge of these new things. So how do we do the intersection? Sorry, union. Start with the union. Let's do the union. So the union, remember, is this up here. Everything that's in A and everything that's in B is in the union. So if you're doing a union here, then you just need everything in A and everything in B. Just write out all of the elements and make sure you don't leave anything out. So like I should have everything in A. That's 1, 3, 5. And I should also have everything that's in B. Now B has 1, 2, 3. We've already written the 1 and the 3. We don't need to write them again. So we just need to add a 2. And that's everything, right? That's everything that's in A and everything that's in B. So that's the union. So let's find the intersection. So the intersection is going to be what we see in this Venn diagram up there. It needs to be elements that are in A and B both at the same time. So you're going to have to look at A and B and say what's in both of those sets, right? So you see a 1 and a 1. So 1 is in both A and B. 1. Then you look at the next one, 3. 3 is in A and B. So let's look at the next one, 5. 5 is in A, 5 is not in B. 5 is not in B, so it's not in the intersection. All right, let's move on to B. We already talked about 1. 1 is in the intersection. Let's talk about 2. 2 is in B. 2 is not in A. So it does not go in the intersection. And let's look at 3. 3 is here. 3 is in both. So 3 is in the intersection, but we already wrote it. So we're done. So that's it. That is our intersection. Okay? So that's how you do an intersection. Let us continue on. So here's another kind of, I'll say definition, but you know, you need to know what it is, but you don't really use it. It's like when somebody says it, you need to know what they mean. So two sets are disjoint. So that's the vocab word, disjoint. So two sets are disjoint if their intersection is empty. Right? So in symbols, A intersect B, and when it equals, A intersect B is the empty set if and only if A and B are disjoint. That's the definition of disjoint, okay? So there's no overlap. Basically, disjoint means the sets do not overlap at all or have no elements in common. Okay, again, it's not a big deal. It's just a definition. What can we do with it? Not a lot. Here's an example. Let's say A is 1, 3, 5. Let's say B is 1, 2, 3. Let's say C is 2, 4, 6. Okay. And then my question is going to be which pairs are disjoint? Which pairs of sets So what are the pairs of sets? You could have A and B, you could have B and C, or you could have A and C. And my question is, which pairs are disjoint? Okay. And so the answer to that question is just going to be, which of these sets have nothing in common, right? So if you're looking at them, like look at A and B. A and B are not disjoint, right? Because they have A has a 1, B has a 1. So trying to get a color here. So A and B are not disjoint. Well, what about B and C? Well, B and C are here. So B has a 1, C does not have a 1. B has a 2, C has a 2. So they have an element in common. So B and C are not disjoint. So then we move on. Let's look at A and C. So A and C. A has a 1, C has no 1. A has a 3, C has no 3. A has a 5, C has no 5. Right? So nothing in A is in C. Nothing in C is in A. So those are disjoint. So we can say A and C are disjoint because the intersection of A and C is the empty set. Because the intersection is the number, or is the elements in common, and they have no elements in common. So that is what disjoint means. Okay, so let's see here. All right, next thing, new definition. Difference, set difference, definition. So A and B are sets again. The difference of sets A and B denoted, it's just A minus B is how it looks. So it is the set of elements that are in A that are not in B. With all elements that are in A but not in B. Oh no. Battery died. Okay, well that's awesome. I'm going to stop recording and then I'm going to start this up and then I'm going to have to splice the video and that'll be terrible. All right, so there should have been a transition just a few seconds ago. What that transition was in the video is that the battery in the iPad died and I had to let it charge for a few minutes. So we have 6% battery life now and it is plugged in, so hopefully it won't die. Of course, it was plugged in a few minutes ago and it did die, so I don't know. But we're going to proceed and hope for the best. Also, it lost some of my written notes, and so I just rewrote the definition of set difference right here. So that's where we're picking up. And yeah, that's where we're picking up. Okay, so something that I didn't say before the iPad died was that, so we have this set difference, which we write A minus B, and it's the set containing all elements of A that are not in B, but there's an alternate notation for it that's right here. So sometimes it's written this way, and that's also the set difference. So this means exactly the same thing as A minus B. Okay, so something I know we didn't do is we didn't write the set builder's notation. So what is A minus B? So the set A minus B is the set of all x such that x is in A and x is not in B. All right, so what does it look like? What does the set difference look like? Well, we can look at the Venn diagram, right? So let's look at the Venn diagram. So come on now. So we got set A, we've got a set B. Here they are. This is A, this is B. So where's A minus B? So it's supposed to be everything in A, but only stuff that's not in B. So you have to be in A and not be in B. So where that is here. This part, right? You're in A, but not B. And that is the set difference. Okay, so you can see why they use the subtraction symbol, or maybe you can't. Let's do an example and then you'll be able to see. So let's say let A be 1, 2, 3, 4, 5. And let's say let B be 2, 4, 6, 8. All right. And I want to find the following. I want to find A minus B, and I also want to find B minus A. Okay. And let's think about how to do this. So A minus B first. And then we're going to do, nope. We're going to do B minus A. B minus A, which is going to be what? Let's find out. Okay. So what do? So the way you should think of this is you're starting, when you're doing A minus B, you're starting with everything in A. There's everything in A. But then what you want to do is you need to get rid of everything that was in B. So we got A minus B, sorry, we have, what I wrote here so far is A, 1, 2, 3, 4, 5. We need to subtract off everything that was in B. So B has 2, 4, 6, 8. So out of what I've got written here, the 2 and the 4 are also in B, right? So those are the two that have to go. So then what is the actual answer here? It's going to be 1, 3, 5. Those are the things that are in A that are not in B. In A, but not B. You highlight this. So we got this, which is equal to this. All right, same thing here. You want to think of, for B minus A, what's in B. So B has, I'm just going to write them up here, 2, 4, 6, 8. And you want to get rid of anything that is in A. So what's in A? We're subtracting A. So we need to get rid of 1, 2, 3, 4, 5. So there's a 2 and a 4, right? These are going to subtract off anything in A. So what are we left with here? Just the 6 and the 8. B was 2, 4, 6, 8. If you subtract off A, you get rid of the 2 and the 4 because they're in A. And that's it. That's how you do set difference, right? It's like subtraction. You start with one set and you subtract off whatever's in the other set. Okay. Yeah. All right. One more basic operation, I think, and then we'll have some identities. So the last basic operation is going to be the set complement. So something we've talked about before was the universe or the universal set. So like all of the stuff outside of A and B, that's the U. Okay. And so I'll write it right here. So we say let U be the universal set. the complement of A, so the complement of the set A, which you write this way, written A with a hat there, is, hold on. Oh, okay. So they want to say it is the complement. You know what? I don't want to say it that way. Is, so basically it's U minus A. Okay. Let me catch up with my writing here. So use the universal set, the complement of the set A, written A with a bar over it, is U minus A. What's that mean? So it is going to be this. So the set is, come on, right, right words. A, the bar over the top, is equal to the set of all x such that like x has to be in the universe and x has to not be in A, right? So what we're using is we're using the definition of set difference to come up with the definition of the set complement here. Okay, so A complement. What this is actually going to be a lot more obvious when we look at the Venn diagram. It'll make a lot more sense. Okay, so we've only got one set here. So there's no A and B, there's just an A. But the rectangle, which we haven't had to talk about before, the rectangle is the U. And so if you want to do U minus A, what you're doing is you're taking everything outside of A. And that is what the set the set complement of A is, everything outside of A. That's how you should think of it. Not going to do a good job coloring in the lines, but it's fine. Okay, so that's the complement. So A complement is everything outside of A. Okay, and that is the set complement of A, or just complement A. All right. Let us see here. Okay, so set identity. So finally, we're on to a different topic. So those are all of our basic operations. Now what we want to do is kind of, how are they related? So identities. All right. So I'm going to bring this up. Well, you can't see what I'm looking at. Oh, you could actually. Now you can't. What I'm doing is I'm bringing up an image. And now that I got the image up there, I've got to erase what I just did. Then I've got to blow this picture up so you guys can see it. And there you go. Those are your set identities. So what are these? So they are just relationships that those rules that we just saw follow. And most of these are actually going to be very, very basic. And they're almost so basic that you can't even prove them. You can, but they're almost so basic that they're hard to prove because you don't even know what to write. I was just resetting the Note app, so hopefully my battery doesn't die. Okay, so like I said, these are so basic that mostly there's not a lot you can do to prove them. Or rather, there's not a lot you have to do to prove them. And so let's look at some of them. So kind of, let's look at a few of these. So let's look at an example. Let's show this one. That example one, show a, what is it? intersect the empty, sorry, intersect the universe should just be A. Okay, should that be true? Yeah, of course that should be true. So the idea here is that if you think about it, you've got the two sets here. So let's look at the Venn diagrams. So first of all, you've got the entire universe. So you've got all of the universe, right? And then also you've got A somewhere. I'm drawing it in a separate Venn diagram because I don't know how to draw it in one so that it'll look nice. So you've got A, which is somewhere, right? And so what you want to know is where do these overlap? And that's going to be the intersection. So the intersection is where they overlap. Well, what's it going to look like where they overlap? Well, the universe is everything, right? The universe is everything. And then A is inside of the universe, right? Should put the U here. A is inside of the universe. So where do they overlap? Well, they're just going to overlap at A. So that's going to be what you get, right? So this is your answer. And of course, that's just going to be A. So when you intersect the universe with any set, you just get the same set back. Okay, and then that's that first identity law. Same thing here with the union with the empty set. The union is every element that's in A and every element that's in the empty set. Well, if you take everything in A and everything in the set with nothing, you're just going to get A back. Okay, so they're so basic that there's not a lot that you have to show. Okay, let's look at some of these others. Yeah. So they have a domination. Domination is not any harder than what we just looked at. Same kind of idea. Maybe let's look at A intersect the empty set. So remember that what you're looking at is actually, let's just do this one without Venn diagram. Let's look at symbols, right? So by definition, A intersect the empty set is the set of all x such that x is in A and x is in the empty set, right? You have to be in both sets. Okay, but then look at this right here. You have to have x in the empty set. What is in the empty set? Nothing, right? But nothing is in the empty set. That's why it's empty. So what do you get? Well, it's just going to be nothing. So when you do the intersection of A in the empty set, you're going to get the set of all x such that x is in A and the empty set, but that's nothing. So you just get nothing. And that's your, whoa, did not know it could draw an arrow. Make a rectangle, stupid. I told the iPad, I said, make a rectangle, stupid. And then it said to me, you make a rectangle, stupid. Like, I'm trying, guys. Okay, so yeah, so you intersect with the empty set, you get the empty set. If you do the union with the universe, you're going to get the universe because you get everything in A and everything in the universe, that kind of thing. If you do a double complement, you get back to the original set, right? Because you're going to be looking at everything outside of the outside of A. We got commutative laws. those things are obvious, but we can look at them a little bit. So A union B is going to be equal to B union A. Why should that be true? Well, because A union B, according to the rules, is the set of all x such that x is in A and x is in B. And B union A is the set of all x such that x is in B. I said and, but this should have been or, sorry. B union A is x such that x is in B or x is in A. But then, of course, from logic that the order doesn't actually matter, right? Between an or, like A or B, B or A, it doesn't matter which is which. So those are going to be exactly the same sets. So same sets. And so that's, what do we have? This one right here. But you can do the same thing for intersection. It doesn't matter, the same kind of thing. So you can write it in set builder's notation and then just say, well, yeah, those are just going to be the same thing. Okay. We got associative laws, which means if you put parentheses, when you do multiple unions, it doesn't matter if you do, like if you want to do A union B union C, you can only do the union one at a time, but it doesn't matter which one you do first. You can do the union of B and C first, or you can do the union of A and B first, and you're going to get exactly the same result. So you can put the parentheses in either place. Same thing with the intersection. It doesn't matter which way you do that. Okay. Distributive laws. The distributive laws work the same way as distributive laws always work. Do I want to do something there? Let me think. I don't think I want to do like a proof of a distributive law, but I think maybe we can look at the, what's it called? The Venn diagram for it. So let's look at the Venn diagrams of what? So let me try to write it the way they write it. So A union B intersect C. And then the other one must have been A union B intersect A union. Sorry, I said union, wrote intersect C. Those are the two, right? Yes, they are. So hopefully we're doing this. Let's see. So let's try to, what are we doing? Intersect union? Union intersect? Union intersect? Okay. Okay. Yeah, those are right. So let's look at the Venn diagrams. So we kind of have to draw like several Venn diagrams, right, to think of our way through these. So here is a rectangle. Here's another rectangle. Do I need two? I don't know. We'll find out. So let's actually just draw. It doesn't matter if A is overlapping B and C at all. But let's draw them so that there is some overlap. So let's call that A, then call that B, bigger, and then let's call this C. So let's say we have A, B, C, and I just realized that what I want is to not have to draw this again, so I'm going to just copy it, duplicate. Okay, so let's think about this. So if we're going to be doing the union here, so first of all, what is B intersect C? So B intersect C is the overlap between B and C. That's so big. Oh, I make small. Okay, so that's this area right here, right? That's the intersect between B and C, the overlap. So then we want to take that and we want to union it with A. So we want to take what we have highlighted now and combine it with all of A. So that's going to be all of A. So we're going to take all of A and just add that in. And that's what it looks like. Okay, so what I just drew was actually all of A union B intersect C. So let's look at the other one. So I guess this can move over here. And we can look at it with this. So let's do this completely separately. We're not going to look at the other one. So we've got A union B. What's A union B? So A union B is everything in A and everything in B combined. So A union B, hold on here. I'm going to need to duplicate this again. Duplicate. We're going to need to draw this twice. Okay, so A union B. So A union B is going to be everything in A and B together. That's going to be this entire circle, that's everything in A, combined with everything in the B circle. Like that, right? So what I just drew was, this is A union B, right? Now let's look at A union C. So let's draw A union C here. A union C. So A union C is everything in A and C. So instead of doing the A and B circles, we need the A and C circles. So let's take everything in A, combine it with everything in C. Okay. And then what we need is, now we need to do the intersection of those two that we highlighted, right? Because we've got an intersection between these two. So let's intersect them. Intersect. What's it going to look like? Well, I'm going to have to redraw it first of all, but I didn't think to duplicate it another time. So we're going to have, let's go, come on, stop. A, I'll draw it a little bigger. B, C. So we've got the A, B, and C. And we're trying to intersect these two that we have here. So the intersection is where what they have in common. So what do these two have in common? Well, what they have in common are, first of all, hopefully you can see that all of A and all of A are included in both of those. So the intersection is what's common. So all of A is common to both. So I know that everything in A for sure is included in the intersection. Okay, what else is in the intersection? Well, hopefully if you look closely, you'll realize that, so this section here, this section is not included, right, in this set. So that means this section has to be blank over here. And down here in C, this is not included in the first set. That means the same portion has to be not included here. But there's kind of a middle section here and here that is included in both of these. So that should be in the intersection. So if I add that to my picture, that's this part right here, right? And so that's what we get. So what I've just done now is I've come up with our set, which was, let's see, what was it? It was A union B, parentheses, intersect A union C. Now, if we compare that to the first set that we came up with, you'll see that those are the same, right? So, same. Okay? Now, that's not a proof. That's just looking at Venn diagrams to try to see what's going on. Okay? But because of that, you can see that these two sets are the same. So that's the one of the what horrible things have happened here. What is this? Oh, this just, okay, hold on. This just somehow got moved. Okay. I was very confused. Okay, so that was just one of the distributive laws, right? So we did the first one, right? Yeah. So that's one of the distributive laws. We also have De Morgan's laws. So just like you have De Morgan's laws for logic, you have De Morgan's laws for sets. So let's just remind ourselves of De Morgan's laws for logic, right? So so recall, in logic, you have De Morgan's law. Logic, right? So De Morgan's law was if you had not like A, oh, we could say A, but no, not P and Q, that was logically equivalent to not P or not Q. And also if you had not P or Q, that was logically equivalent to not P and not Q, right? And then the key thing here is that the symbols switch when the negation goes across. Okay, and we've got De Morgan's laws for sets now. So we have now De Morgan's laws for sets. So what do they say? Well, they're somewhere. It has to do with set complement. So instead of a negation, you have a complement. So like if you do A union B, there's no, this symbol doesn't make sense for sets. So the equivalent of a not is a complement of the whole thing. That's the equivalent of a not. And what is it equal to? Well, you do the complement of the individual sets, but just like before, the symbol is going to switch to the other symbol. Right? And same thing the other way, the same thing for intersection instead of union. If you do the complement of the intersection, it's going to be the individual complements, but then it'll be a union between them. Same thing, the symbol switches, just like it did for logic. Okay, and actually the reason it switches is because of De Morgan's law for logic symbols, right? So like we can actually prove it using logic. Yeah. So let's prove A intersect B is going to be equal to A intersection union B intersection. Okay, let's prove that. So you're not going to have to do a lot of these proofs. We're just kind of verifying these identities. Yeah. All right, let's try this. So let, A and B are just sets. Okay, so let's get started. So when we say A intersect B complement, what is that? Okay, so the idea is this. If you had the intersection of A and B in set builder's notation is the set of all x such that x is in, actually, I'll do it the way the book does it. It's a little bit different than what I was planning. Let me erase this and go back, put the complement back here. So what does it mean to be in the complement of A intersect B? What it means is this. It's the set of all x such that x is not in the intersection. Does that make sense? Because the complement, right? The complement of any set is everything outside of the set. So if you're outside A intersect B, that means X is not in A intersect B. So that's all we're saying here. So we're not dealing with like definition of intersection yet. Okay. So this is just what the complement means. So that's like definition of the complement. Okay, then what can we do? Well, what does it mean to not be, like, what does this mean? Well, what it means is that this is the set of all x such that if you're not in A intersect B, that means, well, we can just write it this way, not x A in intersect B. That's kind of lame to write, but I'm just going to write it that way. Okay, so that's just what it means to not be in A, like not exist in, not exist. That's all. Okay, so I didn't really do anything there. Then what can we do? Well, then what you can do is you can say, well, what does it mean to have the intersection of A and B now? Well, the intersection of A and B, that's all we're looking at. So everything else is the same, X in. What does it mean to be in A intersect B? It means either X is in A, or rather X is in A and X is in B. You have to be in both, right? So this is, if your A intersect B is X in A and X in B. So that's the definition of intersection. Okay. And all of this was really to get it to the point where we had a negation in front of an and. So we have a negation in front of an and, which means we can apply De Morgan's law, the De Morgan's law for logic. So this is De Morgan's law for logic, not for sets, right? So we're looking at applying this rule, not P and Q. Well, we've got not P and Q. So if we apply De Morgan's law, what we're going to get is the set of all x such that not X in A, not X in B, but we know that the symbol is going to flip, right? Because that's what De Morgan's law does, is it flips that symbol. So the and turns into an or. Then what we want to do is get these negations here, the negation back in. So if you have not X in A, not X in A means X not in A. So we can rewrite this as set of all X such that X not in A, or same thing here, not X in B. So that means X not in B, X not in B. Okay. So then we want to look at these symbols now. You've got X not in A. Well, the set of all x such that x is not in A. If you're not in A, then you're in a complement, right? Not in A is a complement outside of A. So this says you're outside of A, and this says you're outside of B. So if you're outside of A, then that means you are in complement. If you're outside of B, that means you're in B complement. So this is definition of complement again. So we've got set of all x such that x is in A complement or x is in B complement. Well, if you're in A complement or you're in B complement, either one, right? All of the x's in A complement, all of the x's in B complement, together, what that makes up is A complement union B complement, right? Because it's everything in A complement, or you're in A complement or you're in B complement. So that's everything in both. Okay, that's a little bit tricky to do, but this is where we arrived. And so what do we get? We get this is equal to this. So that's kind of a proof that just uses the set builder's notation to try to come up with it. It's a lot easier to see if you just look at a Venn diagram, but a Venn diagram is not a proof. You do not have to do this as part of your homework or anything like that. It's just, how would you go about proving these if you really wanted to? Okay, let's see here. So I think that's everything I want to cover. So yeah, so let me just take a peek through here just to make sure there's nothing else that I need. I think there is not, so I'm going to call it right here. Yeah, so that's section 2.2. These are set operations. Actually, how far are we? Well, we're 40 minutes in. 40 minutes in plus the other 20 minutes in, so that's enough. So yeah, so if you have trouble with the homework, then come talk to me in office hours, and I'd be happy to show you how to do any of the problems. And that's it for now. See you on Friday, I guess.